Welcome, ladies and gentlemen, to Parametric Equations of Lines in Space, Example 2. If you need to do so, please pause the video and study this diagram for a little while so you can get adjusted to the three-dimensional view. Let me first read the problem. Compute the parametric equation for the line through the point 2, 1, -1, and perpendicular to the line that's represented by its parametric equations, and the parametric equations for that line, which is labeled as line M. The parametric equations for this line is x equals 1 plus 3t, y is equal to 2 minus t, and z is equal to 3 plus 2t. So these parametric equations represent the line or the vector M. And vector M also contains the points P, R, and S. As we see here, line L is the line that is going through the point 2, 1, -1, and is perpendicular to the vector line M. We're going to use this information to come up with a vector equation that represents that vector line L. The line that goes through 2, 1, -1, and is perpendicular to M. Also notice that I drew a vector through P going to Q to create the right triangle PQR. So we're going to use this right triangle PQR, which I have labeled here the vectors in its vector notation. We're going to use this diagram and its information. We're going to take this three-dimensional section and transform it into a two-dimensional representation in the next pages. So at this time, again, if you need to do so, please pause your video, copy the problem, and study the diagram. And let's get ready to go to the next pages to look at what our solution is going to be. Again, I'm Mr. Davis, the math healer. Thank you for joining me, and let's get started. All right, ladies and gentlemen, we are here and we're starting our solution. So let's go right into the solution and let's examine this. We will make use of the following theorem. This is going to be vitally important to really look at this theorem and understand it, because we're going to use this theorem in order to come up with our equation of that line that passes through the point 2, 1, -1, and that is perpendicular to vector line M. So let's take a look at this theorem. Parametric equations of a line in space. A line L parallel to the vector V, A, B, C, and passing through the point P of x1, y1, z1 is represented by the parametric equations. So let me read that one more time before I pull it up and show the parametric equations. We will make use of the following theorem. I will pull this up a little now. Here we are. Parametric equations of a line in space. A line L parallel to, notice, it's parallel to, it does not have to go through that vector, or the vector does not have to be on that line. The only requirement here is that L be parallel to vector V that has these vector coordinates A, B, C. So L, the sufficient condition is that L has to be parallel to this. V does not have to be on L. All that is required is that L is parallel to this. And passing through the point x1, y1, z1 is represented by the parametric equations. X equals x1 plus at, y equals y sub 1 plus bt, and z equals z1 plus ct. So if you need to do so, please copy this theorem, because we will use this theorem in order to calculate the equation of the line that meets the given requirements of the problem. So we need to understand, again, that vector does not have to be on the line. The only sufficient condition is that the line must be parallel to this, because this will represent that line. So we're going to use a vector that's parallel to L in order to come up with the parametric equations of that line that passes through the given point. So once again, please pause the video, copy this information. Okay, so what we are going to do, as I said before, I was going to take the three-dimensional drawing and write it in a two-dimensional sense. So what I did was I flipped and rotated triangle PQR as it appears here. This line here is line M. So I flipped it and then I rotated it. This is vector line M. Here's P, which is represented as 1, 2, and 3. Here's R. Here's line L. Line L is passing through the point Q, which is denoted as 2, 1, -1, and it is perpendicular to vector line M. And the intersection of those two vector lines is point R. So this is the two-dimensional representation of that three-dimensional figure that you had at the beginning. Now, we want to find a vector V that is parallel to RQ. RQ represents vector line L. And remember from the theorem, the only thing that's required in order to come up with a parametric equation of that line is to find a vector that is parallel to that line. So that vector can be used to represent the equation of that line, because now vectors can be moved anywhere that we would like to put them. Now I could take this vector V and put it directly on top of L. So now let's move on. Well, the next step, here's how I got point P. To get P, I just arbitrarily decided to let T equal 0. So by letting T equal 0, we got the values that X is equal to 1, Y is equal to 2, and Z is equal to 3. So I arbitrarily picked T equal to 0 to get at least 1 point on vector line M that I can use. So that choice of T equal to 0 was just arbitrary. Now remember, we can use the parameter T to generate an infinite number of points on M. For vector M, we were given the following parametric equations. Again, we were given that X equals 1 plus 3T, Y equals 2 minus T, and Z is equal to 3 plus 2T. So we were given that for vector line M. And now we have the direction vector of this parametric equations. So in this case, here A is equal to 3, A times T. For the Y, B is equal to -1, -1 times T. From the Z, we have that C is equal to 2, 2 times T. So from the parametric equations, we have that A is equal to 3, B is equal to -1, and C is equal to 2. We got these values directly from the parametric equations. And you can go back and take a look at the theorem in order to identify what A, B, and C and where they fall in place in the general parametric equations. So again, we had the values A is equal to 3, B is equal to -1, and C is equal to 2. So vector V1 is equal to 3, -1, 2. So I'm calling that vector vector V1. And this vector V1, this vector is parallel to M. So from the parametric equation, we found a vector that is parallel to vector M, or vector line M. We're going to use this vector that is parallel to M. So here's what we know now. We know that vector line M is in the direction of vector V1. Very important. So vector line M has the same direction as vector V1. Here is what we're going to do. We will project PQ onto vector V1. Let me say that one more time. We will project vector PQ onto vector V1. This projection will give us PR. Now, you should have drawn that two-dimensional diagram that I took and that I wrote from converting that three-dimensional figure into a two-dimensional sense. And as you recall, I flipped and rotated that triangle and I wrote it as a two-dimensional figure. So you should have that triangle in front of you so that what I'm telling you here makes more sense as you hear me read this to you. So here is what we know. We know that vector PR is equal to the projection of vector PQ onto vector V1. One more time. So we know that vector PR is equal to the projection of vector PQ onto vector V1. Now, ladies and gentlemen, we will use the projection of PQ onto vector V1 to help us find the vector that is parallel to RQ, vector RQ, so we can then apply the theorem. Now, that's the essential part here. We need this projection because it's going to allow us to find the vector that is parallel to vector RQ that goes through the point 2, 1, negative 1. So recall from the theorem, the sufficient condition in order to write a parametric equation for vector RQ is to be able to find or calculate a vector that is parallel to vector RQ. So we can use that to represent, and notice the key word, to represent the equation of vector RQ. Now, taking a close look at this diagram, again, if you did not copy it, please pause the video and copy it now, because this is going to be essential into what we're going to be doing now. So please pause the video, copy the diagram so you can continue to follow along. Now, as you see from the diagram, by vector addition, we have that RQ, vector RQ, plus vector PR is equal to vector PQ. So by vector addition, I had that vector RQ plus vector PR gives us vector PQ. Now, after applying algebra, I added negative PR to both sides of this equation. I now had that vector RQ can be written as vector PQ minus vector PR. So pause the video and study this for just a little while and go back and take a look at the diagram so you can follow the vector addition of how I got this information. So one more time, vector RQ is equal to PQ minus PR, and I got that directly from the vector equation and using algebra in order to get vector RQ by itself. Now, ladies and gentlemen, if you go back and take a look at your notes, if you copy them as I asked you to do, now we know that PR, though, was equal to the projection of PQ on the vector V1. This is an essential piece of information. So I'm going to just stop here for a while and ask you to go back and take a look at your notes. If you need to do so, please move the video back to where I showed you how did I get this projection here. So this is essential. Again, we know from our previous work now that vector PR is equal to the projection of PQ onto vector V1. So by substitution, we now have that vector RQ is equal to vector PQ minus the projection of PQ on the V1. Well, this will allow us to find vector RQ in terms of vector PQ and the projection of vector PQ on the vector V1. And I see here I forgot to put the vector arrow over PQ, so if you are copying this, please make that correction for me. That was an oversight. That should be vector PQ, not just PQ. Well, now we will now let vector V, the vector that we need to have parallel to RQ. Well, in this case, since we can move vectors anywhere we want them to, we'll let vector V equal vector RQ. And we can do that in math because, again, vectors can be moved anywhere we want them to because their direction will be maintained. So we're going to let vector V be equal to vector RQ. Now, we will use the following projection formula in order to do our calculations. Now, if you saw the introduction video that I have, this will make more sense to you. We're going to use this formula, the projection of vector PQ onto vector V1 is equal to the dot product of vector PQ with the unit vector of vector V1 times the unit vector of vector V1. Now recall that this dot product produces a scalar quantity. And once we do the dot product and generate that scalar quantity, whoa, I had a hard time saying that, that scalar quantity is going to be used to scale the unit vector of vector V1. And we're going to use that. That's going to become our scaling number to scale this unit vector to either enlarge it or to reduce it. Now, let's calculate vector PQ from the two-dimensional diagram that I created. Well, vector PQ is equal to 2 minus 1, comma, 1 minus 2, comma, negative 1, negative 3, because this becomes the terminal minus the initial. So vector PQ is equal to 1, negative 1, negative 4. Now the next thing we're going to do, we're going to calculate the unit vector of vector V1. And vector V1, as you recall, from the given parametric equations, vector V1 is 3, negative 1, and 2. So now using the Pythagorean relationship, the magnitude of vector V1 is equal to the square root of 3 squared plus negative 1 squared plus 2 squared. So the magnitude of vector V1 is equal to the square root of 9 plus 1 plus 4. And finally, the magnitude of vector V1 is equal to the square root of 14. Now, to calculate the unit vector of vector V1, we take the magnitude of vector V1 and we divide the coordinates of vector V1 by its magnitude. So the unit vector of vector V1 is now written as 3 over the square root of 14, comma, negative 1 over the square root of 14, comma, 2 over the square root of 14. So now we just calculated or generated the unit vector of vector V1. Now we will calculate the dot product of vector VQ with the unit vector of vector V1. So the dot product of vector PQ with the unit vector of vector V1 is equal to 1, negative 4. That's the vector that represents vector PQ. This coordinate or vector coordinate represents the unit vector of vector V1. So we're doing the dot product of those two vectors. So the dot product of vector PQ with the unit vector of vector V1 is equal to, we simply multiply each corresponding coordinate and add. So 1 times 3 over the square root of 14. We have that. Now we get a negative 1 times a negative 1 over 14. Well, first, negative times negative is positive. So that becomes plus 1 over the square root of 14. Then here I have negative 4 times positive 2 over the square root of 14. So multiplying that together, we end up getting negative 8 over the square root of 14. Combining our terms, we get that the dot product of PQ with the unit vector V1 is equal to negative 4 over the square root of 14. So here is what we know now, that the projection of vector PQ onto vector V1 is equal to the dot product of vector PQ with the unit vector V1. This scalar quantity is then going to multiply the unit vector of vector V1. And here it is. We have the scalar quantity of this dot product multiplying times the unit vector of vector V1. This becomes our scaling quantity to scale that unit vector. So I have negative 4 over the square root of 14 times, this is not dot product, but it's times 3 over the square root of 14, comma, negative 1 over the square root of 14, comma, 2 over the square root of 14. So now we had that the projection of vector PQ, and I did it again, I left off the vector arrow above PQ. So the projection of vector PQ onto vector V1 is given to us as negative 12 over 14, comma, 4 over 14, comma, negative 8 over 14. Now I can simplify these fractions, and we now have the vector negative 6 over 7, 2 over 7, comma, negative 4 over 7. So now vector V is equal to vector RQ, and we found out that vector RQ is represented by vector PQ minus the projection of vector PQ onto vector R1. Again, so if you need to do so, pause the video and please copy this information here. So here's what we have. Now we have the vector notation that represents vector PQ minus the vector notation that represents the projection of vector PQ onto vector V1. We're subtracting one vector from the other. So now after multiplying this second vector notation through by the negative, we now have 6 over 7, negative 2 over 7, and 4/7. Now we can add the corresponding coordinates of these vectors. So by addition, we have 1 plus 6/7, negative 1 minus 2/7, comma, negative 4 plus 4/7. And after combining, we get that vector V is equal to 13 over 7, comma, negative 9 over 7, comma, negative 24 over 7. So the parametric equation for the line through to 1, negative 1 is now given to us as x equals 2 plus 13 over 7 times t, comma, y is equal to 1 minus 9/7 times t, comma, z equals negative 1 minus 24 over 7 times t. And remember that v represents our vector that is parallel to vector RQ. And from the theorem, we can draw or we can write the equation of a vector line if we have a vector that is parallel to it and we know a point that that line goes through it. So we can use that vector to represent the equation of the line. And that was the sufficient condition of the theorem, is that we need a vector that is parallel to the line and we must know the point that that line goes through. Ladies and gentlemen, please let me know if this instructional video was clear and easy to understand. Thank you for joining me. And my name again is Mr. Joshua Davis. You can find me at mathhealer.com. Thank you for joining me today. Thank you.